Hello everyone. In this video, we'll be covering concepts from the course Chemistry 1412, also known as General Chemistry 2. So I'm going to bring you to a PowerPoint presentation. Where we can discuss the topics that will be covered in this video. So the specific topics that we're covering today are reaction rates, rate laws, reaction orders, and integrated rate laws. Kinetics is the study of reaction rates and how they are affected. Many factors such as concentration, pressure, temperature, and enzyme activity can impact the rate of a reaction. The factors affecting reaction rates that we'll go more in depth with today are going to be concentration, physical state, and temperature. So particles must collide in order for them to react. The higher the concentration of reactants, the greater the reaction rate. A higher concentration of reactant particles allows for a greater number of collisions. So think about that as a real-world aspect. So the more people you have in a room, the more likely you are to bump into them, which is the same way with having more reactant particles and allowing them to bump in or have collisions with each other. The physical state of a reactant influences the reaction rate. Substances must be able to mix in order for those particles to collide. The higher the temperature, the greater the reaction rate. At higher temperatures, particles have more energy and therefore can collide more often, allowing them to become more effective. So now we're going to express the rate of a reaction using equations. Reaction rate is measured in terms of change in concentration of reactants or products per unit time. So for a general reaction, we're going to have our reactant A yielding our product, which is going to be B. The rate equals the change in concentration of either our A or B, so our reactants or products, over the change in time. So as you can see, it can be represented by two different formulas. If you're using your reactants, which is A, you're going to have rate equals negative change in the concentration of A or your reactants over the change in time. Or if you're using your products, you have change in B, which is your products, over the change in time. No matter which one you choose to use, you will get the exact same answer. Your rate of your reaction will be expressed in molar per second. This is because we're dealing with concentration and time. The negative sign is used because the concentration of A is going to be decreasing as the reaction moves forward. This gives the rate a positive value. So now we're going to go through our first example. I have a general reaction, which is A producing B, where at temperature 0, the concentration of A is 1 molar and the concentration of B is 0 molar. If at time 2, our concentration of A has decreased to 0.98 molar and the concentration of B has increased to 0.02 molar, what is the average rate of reaction for this reaction? So we're going to move to our boogie board to work through both ways of how to solve this problem. So first thing, write out what we have. So we know at T equals 0, our concentration of A equals 1 molar, while our concentration of B equals 0 molar. At time 2, our concentration of A equals 0.98 molar, and our concentration of B equals 0.02 molar. So let's work with our reactants first. So our equation using our reactant information was rate, which I'm going to represent with an R, equals negative delta A, which is the change in concentration of A, over delta T, which is the change in time. So now we can plug in our actual numbers to get our answer. So our change, so let me go ahead and just erase that right here. So our change is going to be 0.98, so 0.98 minus 1. This is because change is going to be your final minus your initial. You're then going to have the change in time, which is 2 minus 0. When you plug this in, you get the whole thing. The negative will just carry over, and it's going to be negative 0.02 over 2. The two negatives will end up canceling out to form a positive value. So your rate is going to be 0.01 molar per second. And that's what we get when we plug in our reactant information. Now we can do the exact same thing, but this time we'll use our product information and see how it relates to our rate. So rate equals the change in concentration of B over the change in time. So we can plug in 0.02 minus 0 over 2 minus 0. When we plug this in, we have rate equals 0.01 molar per second. So as you notice, we get the exact same answer no matter which way we decide to plug it in. And this should happen no matter what information you're given. So let's go ahead and move back to our PowerPoint presentation where we can cover more information. Now we're going to discuss reactions that have coefficients. A coefficient is the number that you're going to see in front of the compound that you're dealing with. So it's going to be represented with the little or lowercase alphabet letters. So when we move down to our rate and how we're going to set it up, we plug it in by doing 1 over the coefficient. When you're using your reactants, you have to ensure that you plug that negative sign in there. Your products will be set up the same way, just it won't have that negative sign. So now we can work an example where we can practice solving and setting up our rate equation. So we have O2 forms at a rate of 9.0 times 10 to the negative 6 molar per second. Using the following reaction, determine the rate of formation of NO2, the rate of decomposition of N2O5, and the reaction rate for the following reaction. So let's switch over to our boogie board. All right, so the first thing I like to do is just to write out what my reaction is. So we have 2N2O5 yields 4NO2 plus O2, and they told us that our rate of formation for O2 is going to be 9.0 times 10 to the negative 6 molar per second. And so for part A, they want us to determine the rate of formation of NO2. So what we're doing is we're comparing NO2 to our O2. So we're comparing this to this. So they're both products. What we know is that as we increase in 1 mole of O2, we're going to increase 4 moles of NO2, and we know that because of the coefficients. So what we can do is simply multiply the rate of formation of our O2 times 4. So 9.0 times 10 to the negative 6 times 4 will give us 3.6 times 10 to the negative 5 molar per second. And this is going to be the rate of formation for NO2. For part B, we're dealing with the decomposition of N2O5. So N2O5. So we're comparing our N2O5 to our O2. So we're now comparing a reactant to a product. So we can set this up the same way that we set up part A. So we know that for every 1 mole of O2, so which would be, we can plug in our reaction rate for O2. We are decreasing by 2. But if we want, we can simply plug in times 2, but our answer has to be negative. So you'll do 9.0 times 10 to the negative 6 times 2 equals negative 1.8 times 10 to the negative 5 molar per second. So what this means is that N2O5 is decreasing by 1.8 times 10 to the negative 5 molars per second as our products are increasing. So now I'm going to go ahead and erase this. We can start to write our reaction equation out. So I'm just going to write using every single thing that we have in this reaction. First being our reactant. So remember, reactant has the negative. We put 1 over the coefficient, which was 2, and that's the delta N2O5 over delta T, and that's going to be equal to 1 over 4, which was our coefficient, times the change, or delta NO2, over delta T equals, and for our O2, since it has a coefficient of 1, we can either leave out the fraction or we can put 1 over 1. So we can put 1 over 1 delta O2 over delta T. So as you can see, they're all equal to each other, which means when we plug them in, we should get the same number for the rate of the reaction. So let's go ahead and plug in everything that we just calculated. So we have rate equals negative 1/2 over, and what is going to go here is what we calculated in part A and B. So for the N2O5, we had a negative 1.8 times 10 to the negative 5 equals 1 over 4 times 3.6 times 10 to the negative 5 equals 1 over 1 times 9.0 times 10 to the negative 6. So what you'll notice when you plug them in is that we get a rate of 9.0 times 10 to the negative 6 for each of our rates, and that's molar per second. And that's how we'll set it up. It's pretty easy to tell for this one because we have our O2 has a coefficient of 1, so we know that our rate is going to be whatever the rate of formation is for that compound. However, not all of your examples will have coefficients of 1, so it is good to know how to actually set this up. So let's go ahead and go back to our PowerPoint presentation. And we can move on to rate law. So the rate law equation is rate equals K, which is the rate constant, and it's specific for a given reaction at a given temperature. So depending on the example that you're working, it can be different for each one. And that's going to be times the concentration of A to the power of X, which is going to be a reaction order, and these are determined by experiment. It is not the coefficient, it is the reaction order, times the concentration of B to the Y, which is B's reaction order. If you add the reaction orders for A and B, you will get the overall reaction order. So the overall reaction order is going to be where you simply add all the reaction orders that you have determined up. So let's say that X is 1 and Y is 2. So if I have 1 plus 2, my overall reaction order will be to the third order. And we'll go through how to actually determine those orders now. A reaction has an individual order with respect to or in each reactant. If a rate doubles when the concentration of A doubles, the reaction is a first-order reaction. And as you can see, it's the concentration of A to the 1. If the rate quadruples when A doubles, the reaction is a second-order reaction. And so you have A to the 2. If the rate does not change when A doubles, the reaction order is simply the concentration of A. So now we're going to do a little checking for understanding. So there are 3 different examples, and they want you to write the rate equation for each of the following cases. For each example, state the overall order of the reaction. So for part A, the reaction A plus 2B equals C plus D, where the rate of reaction is not affected by the concentration of A, but is proportional to the square of the concentration of B. So what we get is A to the 0, so A to nothing, so we don't have to put A there. Remember that we have K, rate equals K times the concentration of A to its power, B to its power, or its order, is proportional to the square of the concentration of B. So we have the concentration of B to the second order. The overall order is 2. 0 order with respect to A plus the second order with respect to B. So you have 0 plus 2 gives you 2. Now we'll move on to B. The reaction 2A plus B equals 2C plus D, where the rate is proportional to the concentration of both A and B. So what we get is that both of them are to the first order. So we have rate equals K, concentration of A, concentration of B. Our overall reaction order will be 2. That is because you would have a 1 and a 1. Now we have C. The reaction 2A equals 2B plus C, where the rate is proportional to the concentration of A. So we have rate equals Ka, where the overall order is 1. So because we don't have another reactant, we just have A. So we just have rate equals Ka. So now I'm going to show you a quick video on how to actually find the order of a reaction based off of an experiment.
Let's take a reaction where A plus B gives us our products, and the lowercase a and the lowercase b represent the coefficients for our balanced equation. It makes sense that if we increase the concentration of A and B, right, A and B would be closer together in space and more likely to react, therefore increasing the rate of our reaction. And this is true for most reactions. If you increase the concentration of your reactants, you increase the rate of your reaction. We can check this by doing some experiments. So let's say we want to figure out what the effect of the concentration of A has on our rate of our reaction. So we're going to hold the concentration of B constant. So we hold the concentration of B constant in our experiments. We change the concentration of A, and we see what effect that has on the rate of our reaction. We're going to use the initial rate of the reaction, and that's because as our reaction proceeds, the concentration of products will increase. And since reactions are reversible, if we have some products present, right, that can affect the rate of our reaction. And that's not our goal. Our goal is to figure out what effect the concentration of our reactants has on our rate. And so we use the initial rate, where we have only reactants present and no products. So in our first experiment, let's say the concentration of A is 1 molar, and the rate of our reaction, the initial rate of our reaction, is 0.01 molar per second. And in our second experiment, we increase the concentration of A to 2 molar. We hold the concentration of B constant, and we observe the rate of our reaction to increase to 0.02 molar per second. So we've increased the concentration of A by a factor of 2. And what happened to our rate? Our rate went from 0.01 to 0.02. So the rate increased by 2 as well. All right, let's compare our first experiment with our third experiment now. We're going from a concentration of A of 1 to a concentration of A of 3. So we've increased the concentration of A by a factor of 3. And what happened to the rate? The rate went from 0.01 to 0.03. So the rate increased by a factor of 3. All right, to figure out the relationship, you have to think to yourself, 2 to what power x is equal to 2. Obviously, that would be 2 to the first. 2 to the first is equal to 2. All right, we could have done it for our other comparison as well. 3 to what power x is equal to 3. Obviously, 3 to the first is equal to 3. So the rate of our reaction is proportional to, that's what this funny symbol means here, the rate of our reaction is proportional to the concentration of A to the first power. All right, let's do the same thing for the concentration of B. So we do some experiments where we change the concentration of B, and we see what effect that has on our initial rate. So for all of these, we're going to hold the concentration of A constant. Therefore, whatever we do to B is reflected in the rate of our reaction. So in our first experiment, the concentration of B is 1 molar, and the rate is 0.01 molar per second. And then we change the concentration of B to 2 molar, right? We double the concentration of B while holding the concentration of A constant. And we observe the initial rate of our reaction to be 0.04 molar per second. So we've increased the concentration of B, not A. Let me change that. We've increased the concentration of B by a factor of 2. We've gone from 1 molar to 2 molar. And what happened to the rate? The rate went from 0.01 to 0.04. So we've increased the rate by a factor of 4. Let's compare our first experiment with our third experiment now. We're going from a concentration of B of 1 molar to 3 molar. So we've increased the concentration of B by a factor of 3. And what happens to the rate? The rate goes from 0.01 to 0.09. So we've increased the rate by a factor of 9. So now we think to ourselves, 2 to what power, I'll make it y, 2 to what power is equal to 4? Obviously, y would be equal to 2. 2 to the second power is equal to 4. Or 3 to what power y is equal to 9? Obviously, 3 to the second power is equal to 9. So we've determined that the rate of our reaction is proportional to the concentration of B to the second power. All right, now we can put those together. We can put these together to write what's called a rate law. Okay, so we know that the rate of our reaction is proportional to the concentration of A to the first power, and we know that our rate is proportional to the concentration of B to the second power. And then we put in what's called a rate constant here, K, and this represents our rate law. So let's go through these one by one here. So capital R is the rate of our reaction, right? This is the rate of our reaction, right? K is what's called the rate constant. So this is the rate constant. And there's a difference between the rate of our reaction and the rate constant. If we change the concentration of our reactants, we change the rate of our reaction. But if we change the concentration of our reactants, we don't change the rate constant, right? This is constant. It does depend on the temperature, though, so we'll talk about that in later videos. Here we have that the reaction is concentration of A to the first power. We say the reaction is first order in A. So we say that our reaction is first order in A. And we found that it's second order in B, right? So we had a 2 here. So this is second order in B. And we can also talk about the overall order of our reaction. So for first order in A, right, we're first order in A and second order in B, the overall order would be 1 plus 2, which is equal to 3. So the overall order of our reaction is 3. All right, let's go back up here to the general reaction that we started with. All right, so let's go right back up to here. We have this. Let's write a general rate law. So if this is your reaction, your general rate law would be R is equal to your rate constant, right, times the concentration of A to some power, I'll make it X, times the concentration of B to some power, which I will make Y. And the reason why I'm showing you this is to show you that you can't just take your coefficients, right? You can't take your coefficients and stick them into here, right? So it doesn't work that way. You have to know the mechanism of your reaction. So these orders have to be determined experimentally. So you have to look at your experimental data here. And the orders affect the units for your rate constant. For example, let's go back down to here, and let's figure out the units for the rate constant for this example. So the rate of our reaction, right, the rate of our reaction was in molar per second, right? This is molar per second. We're trying to find the units for K. The units for concentration are molar, right? So this would be molar, and then this would be to the first power, and this would be molar to the second power. So we'd have molar to the second power. All right, so solving for K, right, you could just go ahead and cancel out one of these molars right here and solve for K. So you would get, this would be 1 over seconds now on the left, so 1 over seconds, right, and divide by molar squared, so 1 over seconds times molar squared, or you could write this 1 over molar squared times seconds. So those would be your units for K for this reaction, right, with an overall order of 3. But it can change, right? It can change depending on the order. Now let's look at this reaction. We have only one reactant A turning into our products. And if we look at the two experiments, in our first experiment, the concentration of A is 1 molar, and the initial rate of reaction is 0.01 molar per second. If we double the concentration of A to 2 molar, the rate stays the same. It's still 0.01 molar per second. So even though the concentration of A is going from 1 molar to 2 molar, right, that's doubling the concentration or increasing the concentration of A by a factor of 2, the rate stays the same. So you could say the rate, it's the rate times 1 because it's the same rate. So 2, right, so 2 to what power x, 2 to what power x is equal to 1. Obviously, x would have to be equal to 0. 2 to the 0 power is equal to 1. So any number to the 0 power is equal to 1. So this reaction is 0 order. It's 0 order in A. And if we wanted to write our rate law, we would write the rate of the reaction is equal to the rate constant K times the concentration of A. We have only one reactant here. And since this is 0 order in A, right, we could just write the rate of the reaction is equal to the rate constant K. And so if you wanted to know the units for the rate constant K, well, the rate is in molar per second. And so those would also be your units for K. K would be in molar per second. So here's an example of how your units for K change depending on the overall order of your reaction.
All right. So now that we have covered that, we can go back to our PowerPoint presentation for Integrated rate laws. An integrated rate law includes time as a variable. We're going to cover first, second, and zero order rate equations. So the first order rate equation is going to be Ln of the concentration of A initially over the concentration of A as its final concentration equals K, which is our constant, times time. The second order rate equation is going to be 1 over the final concentration of A minus 1 over the initial concentration equals KT. And then we get to the zero order rate equation, which is going to be the concentration of A final minus the initial concentration of A equals negative KT. So now we can work through an example where we actually start to use our integrated rate law equations. The decomposition of nitrogen dioxide to nitric oxide and oxygen is a second order reaction. So that is a hint on which equation to use, second order reaction, with a rate constant of 0.54 molar to the negative 1 seconds to the negative 1 at 300 degrees Celsius. If the initial concentration of NO2 is 0.008 molar, what is the concentration of NO after 20 minutes? And then they give you the reaction right below. So we're going to go ahead and switch to our boogie board so we can work through this example. All right, so let's write out what we have. So we have 2NO2 goes to 2NO plus O2. We know that this is second order, which allows us to know which equation to use. We know that our K, which is our constant, is 0.54. We know that our initial concentration of NO2 is going to be 0.008 molar. We're looking for our final concentration, and our time is 20 minutes. All right, so let's write out what our equation, which equation we are using. So we have a second order, which is going to be 1 over the final concentration minus 1 over the initial concentration equals KT. And so we can plug in the variables that we know so that we can try to figure out how to solve for the missing variable. So we have 1 over NO2, which is what we're looking for, minus 1 over 0.008 equals, this is molar, equals 0.54, 1 over M times S, times, and it's going to be time, but we need it in seconds, not minutes. So if you do 20 minutes, and we know that for every 1 minute, we have 60 seconds, this will give us 1,200 seconds. So we have 1,200 seconds that we need to plug in. All right, so our seconds can cancel out, and we can go ahead and start doing our math. So let's do 1 over NO2 minus 1 over 0.008 equals, if I do the math on this side, so the 0.54 times 1,200, I'm going to get 648. We then can do our 1 over 0.008, so we'll get 1 over NO2 minus 125 equals 648. We can add 125 to both sides, So we have 1 over NO2 equals 773. So that was adding 125 to both sides. And then I can't forget about this 1. So I do NO2 equals 1 over 773, which is going to give me 0.0013 molar. And this would be my final answer. So that would be my final concentration of NO2 after 20 minutes. All right, let's go back to our PowerPoint presentation. And we can do another example. So this one is going to be set up pretty much the same way, however, it's going to be a different order. The conversion of cyclopropane to propene is a first order reaction with a rate constant of 6.7 times 10 to the negative 4 seconds, so 1 over seconds, at 500 degrees Celsius. So we're going to do A and B. So right here, there's supposed to be a little b. If the initial concentration of cyclopropane is 0.05 molar, what is the concentration of cyclopropane after 30 minutes? So we're going to do part A first, and then we can jump right into part B. Part B says, how long does it take for the concentration to reach 0.01 molar? So let's move to our boogie board so that we can work through this problem. So we're going to do part A first. So this is what we know. We know that we have a first order reaction. We know that our K is equal to 6.7 times 10 to the negative 4. We know that our initial concentration of cyclopropane, which is C3H6, is going to be 0.05 molar. We're looking for final concentration, and we know we have a time of 30 minutes. All right, so we can set this one up just like we set up the first problem that we worked through. However, the equation that we're using is different because now we have a first order reaction. So for first order, we have Ln of the initial concentration over the final concentration equals Kt. So we're looking to be able to get our final concentration by itself. Sometimes it's easier to manipulate the equation before you start plugging in. Sometimes it's not. So just for the people that would like to manipulate the equation, I'm going to show you how to convert it. So we want to get our final concentration by itself. The first thing I want to do is to get rid of the Ln. To do that, I bring it to, hopefully you guys have the little calculator. It's e to the x. So if you do second e to the x, it will bring it to look like the original concentration over the final concentration equals e to the kt. All right, and then I need to get my final concentration by itself. So I do A T, which is the final concentration, equals the original concentration over e to the kt. All right, so now we can start to plug everything in. So we say that we have C3H6, which is going to be our final concentration, equals our initial concentration, so the 0.05 over e to the k, which is going to be our 6.7 times 10 to the negative 4 times t, which is in minutes, which we need to convert to seconds. So if we're doing 30 minutes, for every 1 minute, we have 60 seconds. This is going to give us 1,800 seconds. So we're going to plug 1,800 in for our time. And then you can slowly work piece by piece. So if you do the concentration of C3H6 equals 0.05 over, when you plug the bottom portion into the calculator, you should get 3.3401. You then plug that in, and you have the concentration of C3H6 equals 0.015 molar. And that will be your answer for part A. Now, for part B, so let me erase this and we'll go slightly over so you can remember. They want to know how long it takes for the concentration to reach 0.01 molar. So now we're solving for time. So let's rewrite out what we have. So we know it's first order. We know that K equals 6.7 times 10 to the negative 4. We know our initial concentration is for C3H6 is going to be 0.05. They want to know how long it takes for it to be able to get, so this is our final concentration, to 0.01 molar. And we don't know time. Time is what we're going to be solving for. So we do ln of our initial concentration over our final concentration equals kT. So we do ln of 0.05 over 0.01 equals K, which is 6.7 times 10 to the negative 4, times time. So we can plug everything on our left side in, and we get 1.609 equals 6.7 times 10 to the negative 4 times time. We then can divide using algebra, so we simply divide both sides by 6.7 times 10 to the negative 4, and we will get 2,402 seconds, and that's going to be our time. Some problems might want you to convert this to minutes, then you would just simply do the basic conversion that we did when we converted time the first time. So in place of going from minutes to seconds, you would go from seconds to minutes. So let me go ahead and erase this and move back to our presentation. So now we've covered our 4 topics. So we covered reaction rates, where we discussed how concentration, temperature, and physical state can affect the rate of a reaction. We discussed the rate law and reaction orders, so first, second, and zero order. We also talked about how to find the overall order, which is once you determine what your orders are for each of your components in your reaction, you just simply add them up and you have your order of your reaction. And then we discussed integrated rate law, which is what you'll see a lot on your exams, and we worked through a couple examples. This is all that we have for today's presentation. I highly suggest that if you're struggling on this concept, that you go and see or use the resource of Khan Academy, which is the person that had spoke in that video that I had showed you. And then using your textbook is another good resource. I know not very many college students like to use it. However, it is, you paid for it, you might as well use it. Until next time, thank you and have a good day.